Students, I am Mr. J. Arruldoss, St.Joseph College of Arts and Science, Department of Mathematics. Now we are going to see some definition and theorem on matrices. Unit 5, BSc Mathematics, third year students, linear algebra. Definition for trace. If T belongs to A of E, then trace of T is the sum of the characteristic roots of a matrix M1 of T. Next we see a lemma. If T belongs to A of E, then trace of T is the sum of the characteristic roots of T, using each characteristic root as often as its multiplicity. Proof. Assume that T is a matrix in Fn if K is the splitting field for the minimal polynomial of T over F. Then by theorem 662, that is, if T belongs to F, we have all its characteristic roots lambda 1 to lambda k in F, then a basis of V can be found in which the matrix of T is of the form J1, J2 and so on Jk, all in the diagonal, where each Ji is equal to Bi1, Bi2 and so on Bi Ri, all in diagonal, and where Bi1 to Bi Ri are basic Jordan blocks belonging to lambda I. In Kn, T can be brought to its Jordan form J. J is a matrix on whose diagonal appear the characteristic roots of T, each root appearing as often as its multiplicity. Thus, trace of J is equal to sum of the characteristic roots of T. Since J is of the form ATA inverse, trace of J equal to trace of T. Thus completes the proof. Next we see another lemma. If F is a field of characteristic roots, characteristic 0, and if T belongs to A of E is such that trace T power I is equal to 0 for all I greater than equal to 1, then prove that T is nilpotent. Since T belongs to A of V, T satisfies some minimal polynomial P of x equal to x power m alpha 1 x power m minus 1 plus and so on alpha m from T power m plus alpha 1 T power m minus 1 plus and so on plus alpha m minus 1 T plus alpha m equal to 0. Taking traces on both sides, we get trace of T power m plus alpha 1 trace of T power m minus 1 plus and so on plus alpha m minus 1 trace of T plus trace alpha m equal to 0. Since trace of T power I is equal to 0 for I greater than or equal to 1, we get trace alpha m equal to 0 if dimension of V equal to n, comma, then trace alpha m equal to n into alpha m, whereas n into alpha m equal to 0, but the characteristic root of f is 0, therefore n is not equal to 0. Hence it follows that alpha m equal to 0. Since the constant term of the minimal polynomial of T is 0, by theorem we have, if E is finite dimensional over F, then T belongs to A of E is invertible if and only if the constant term of the minimal polynomial for T is not 0. From this we get that T is singular, and so 0 is a characteristic root of T. Consider T as a matrix in Fn and also as a matrix in Kn, where K is an extension of F, which in turn contains all the characteristic roots of T. Again by a theorem we have, If T belongs to A of V has all its characteristic roots in F, then there is a basis of V in which the matrix of T is triangular. From this we get in Kn we can bring T to triangular form, and since 0 is the characteristic root of T, it is of the form 0 0 0 0 0 and so on 0, B2 alpha 2 0 0 0 and so on Bn star and so on alpha n, which is equal to, which can be restricted to 0 star 0 T2, where T2 equal to alpha 2 0 0 0 0 so on 0 star and so on alpha n is a n minus 1 cross n minus 1 matrix. The star indicates the parts in which we are not interested in the explicit entries. Now T power k equal to 0 0 star T to k. Hence 0 equal to trace of T power k, which is equal to trace of T2 power k. Thus T2 is an n minus 1 cross n minus 1 matrix with trace of T power k equal to 0 for all k greater than or equal to 1. Either using induction on n or repeating the argument on T2 for T, we get alpha 2 to alpha n are the characteristic roots of T, which implies alpha 2 equal to alpha 3 equal to and so on alpha n equal to 0. Thus, when T is brought to a triangular form, all its entries on the main diagonal are 0. Therefore, T is nilpotent. Thus, we have proved. Next, we are going to see an important lemma, that is Jacobson lemma. If f is of characteristic 0 and if S and T in A of E are such that St minus Ts is nilpotent, that we have to prove. For the proof, for any k greater than or equal to 1, we define St minus Ts the whole power k, which can be written as St minus Ts the whole power k equal to St minus Ts the whole power k minus 1 into St minus Ts. That is equal to St minus Ts into k power minus k minus 1 into St minus St minus Ts power k minus 1 into Ts. Since St minus Ts commutes with S and St minus Ts the whole power k minus 1 into St equal to S into St minus Ts the whole power k minus 1 into T. Here we consider B as St minus Ts the whole power k minus 1 into T. Then St minus Ts the whole power k can be written as Sb minus Bs. Hence, trace of St minus Ts the whole power k equal to trace of Sb minus trace of Bs, which is equal to 0. By previous lemma, we get St minus Ts is nilpotent. Thank you.